sorry. Tropical storms might come through, or some sort of event might come through, but the bigger the event gets, the more exponential the damage is, the more exponential the impact is. So these extreme events are what we really want to focus on. And then sort of why, sort of additional reasons are when you couple an extreme event with existing environmental stressors or low frequency trends, there's a potential to serve as a change point, right? So this thing pushes a system over the threshold, and it's not linear. It doesn't just bounce back. It sort of shifts the system into a new paradigm. And so part of this worry about extreme events is that our ability to assess risk and vulnerability is limited by our ability to predict them. And so this is particularly important in coastal areas where there's lots of growing human populations, there's lots of growing infrastructure, and as a result of that, we're naturally stressing the environment. And so all these things sort of come together in a big way in the coastal zone. And as you can kind of see here, today is, got it. Today's talk is going to be focused on the extreme event of tropical cyclones. And this was an image of Hurricane Michael making landfall in the Florida Panhandle. And you can see this is absolute devastation in this area. And so the potential for human death and property damage is on the extreme side for these types of events. So how does the ocean relate to tropical cyclones? Well, the sea surface temperature is what allows the ocean to transfer its energy to the atmosphere. And so the sea surface temperature is a key parameter that we're often looking at when we're talking about tropical cyclone intensification. But sea surface temperature is inevitably linked to the subsurface structure underneath it. The layering of the ocean matters to sea surface temperature. And so what you can see here is sort of just some images of just two different water columns, one that has relatively shallower, colder water, and one that has relatively deeper warm layer. And as a result of that difference, the sea surface temperature underneath a tropical cyclone, arrow, the sea surface temperature, this sort of blue versus yellow, suggests there's potential for notable differences in the sea surface temperature underneath a tropical cyclone related to the layering of the ocean underneath it, right? So the subsurface conditions are important for the energy transfer from the ocean to the atmosphere. And so where I'm really interested in is the continental shelf, because this is where storms are going to likely encounter humans and human infrastructure, right? So the coastal zone, the continental shelf, this is where these storms are going to have to pass through in order to make a landfall. And so understanding the intensification processes in the coastal zone are something I'm very interested in, and that's what this talk is largely about. But before we get into the coastal zone, let's just take a step back and look at what happens in the open ocean, right? So in the open ocean, kind of have my very PowerPointy cartoon here, where we have sort of an open ocean water column where you have sort of an upper warm layer, and underneath that there's stratification, and you have a cold lower ocean. And so when a storm comes through, there are a couple ways in which it can modify the sea surface temperature. The two that I'm going to focus on are heat loss through surface fluxes. So this is sort of outgoing heat that is emitted from evaporation. So when water changes state, right, when you go from liquid water to water vapor, there's a tremendous amount of energy that needs to be pulled out of the ocean to get that state of matter change to happen, right? So this is a primary way in which tropical cyclones get their energy is evaporation. But there's also something called sensible heat flux, which is basically the fact that the atmosphere and the ocean are different temperatures, and things that are in different temperature conduct heat, right? There's this transfer of heat when you put two things that are of different temperature together. So there are these two mechanisms that allow heat to go from the ocean to the atmosphere and energize these storms. The other way in which storms tend to, or another way in which storms tend to change the sea surface temperature, is through direct mechanical mixing. So there's lots of waves, there's lots of wind that stir up the ocean. And so you basically get the upper warm layer gets mixed down into the colder warm layer. And so you're transferring heat from the upper ocean to depth, and colder water from below gets mixed upwards. And in the open ocean, you can think of the ocean as this infinite cold pool, right? The extent to which a hurricane is going to mix the ocean is going to be on the order of hundreds of meters. The open ocean is thousands of meters. So that effectively creates a situation where the cold water that's cooling the surface is effectively infinite. You can keep on mixing cold water up into the upper ocean and cooling this surface, right? And that's a really important factor because this is sort of a negative feedback loop. The stronger a storm gets, the more mixing it's going to drive. The more mixing it drives, the colder the sea surface temperature is going to get, the less energy is going to pass into that storm. So it acts as a brake on these storms, right? So this is a really important mechanism to potentially limit the strength of a storm. So we sort of have to ask ourselves, what changes when we get to the coastal ocean? Oh, sorry, I skipped a step, right? So this mixing is kind of cool. You can see these cold wakes from the tropical cyclone mixing as these storms pass through, right? So what you're seeing here is the sea surface temperature image of a cold wake, basically. So you can see the white. I'm having trouble with the mouse here. Sorry, guys. Here's the mouse. You can see the sort of the trace here in white. Mouse is not visible. You guys can't see that, can you? Okay, well, there's a trace of where the storm went, and underneath that trace is a cold tongue. That's this cold water that's been mixed up by the storm. And for many of the folks in the room who may not care about ocean physics, this cold wake has biological implications, right? So this stirs up nutrients, right? So the nutrients that come up from depth get into the photic zone and can create phytoplankton blooms. So these cold wakes are often associated with phytoplankton blooms. And while I don't keep up with the literature, there is a debate about whether or not globally the photosynthesis that's associated with cold wakes has a significant impact on global primary production. So it's not that's not necessarily a trivial thing or just kind of a flaky thing. There is some debate about whether or not there is significant impact on global primary production from tropical cyclones. But that's sort of a sidebar. I'm here more to tell you about ocean physics, right? And so we do see these cold wakes in the ocean. And so the question, as I kind of preceded this slide with, was what changes when we get to the coastal environment? Well, the most obvious thing for me was there's a bottom boundary layer, right? So the shelf has depth limitations. We start running into the bottom here. And why is that important? Well, when we have a bottom, which I can't really point to here. So in this little cartoon, when we have a bottom, the infinite cold reserve is no longer applicable, right? We have a hard cap on how much cold water we can mix to the surface, right? So that lack of infinite cold reserve presents a potential issue where once you mix this bottom water up, there's no more cold water to continue cooling the sea surface, right? And so this sort of sets up a question of, if the shelf is preconditioned in a particular way, there may not be that cold regulator to limit the intensification of a storm. And so that's basically what this talk is going to focus on, is what are the sort of cascading or sequential events that can lead to setups that are important for intensification. And the type of intensification I'm really concerned about is rapid intensification. And I don't think it's probably a hard sell to people in this room why we might care about rapid intensification, right? Storms changing really fast in a short amount of time is bad for business, right? It's hard to get people, to evacuate. It's hard to board up buildings, protect infrastructure when things change very rapidly. So the rapid intensification of tropical cyclones is a critical weather issue. And so this is sort of satellite imagery of actually Hurricane Sally. And you can see sort of one was meandering here off the coast of the southeast here. It's sort of, I want to say malformed. I don't know if that's the greatest terminology in the world, but it's not well defined. The eye is not critically developed here. And then you can see several, I think it's probably a day or two later, that eye wall has formed up, and we have a much more intense event going on here as it's transiting the shelf, right? And so much of the work on rapid intensification has occurred in the open ocean, right? And so a lot of the work in general in hurricanes is in the open ocean, and there's much less work done in the shelf environment. And so some of this work is to try to better understand how things change when you get into a coastal environment, when there's bottom constraints and other dynamics that are different than the open ocean. And so the overall goal here is to improve the understanding of the sequence of events that impact storm systems over continental shelves. And as I sort of alluded to, I'm going to focus on quantifying sequences of events that lead to anomalously warm shelves, because warm shelves are associated with intensification. And so a couple years ago, during Hurricane Michael, we had this sort of epic storm that went from a category 4 as it was crossing the shelf to a category 5, right? And that's kind of like unprecedented. Category 5 storm making landfall is extremely rare. And that's typically not what you see. And so during that time period, I was sort of looking at things, and I kind of came up with this idea that, if you have so this little sort of cartoon sort of shows you the conceptual idea of ways in which storms can interact in unexpected and potentially extreme ways. Where we have the plot A there is we have a warm surface, and an arrow would help. I don't know if you can, anyway, you can see the warm surface layer on the top of that plot, and then the cold bottom layer, which is sort of what we normally expect in the summertime. The surface heats up and the bottom stays cold. If you get, say a baby storm come through, or just some mixing event, that's going to take the heat that's in the upper ocean, pump it downward, and it's going to take the cold water and move it upward, homogenizing the water column and basically pumping heat to depth. And so we've now cleared the shelf of cold water. If that's followed by a period of anomalously warm temperature conditions, we reheat the upper ocean, and now we have a extremely warm upper ocean on top of a warm lower ocean, and we have extreme heat content, which the storm can thrive on, right? And so this appeared to be the case in 2020 during Hurricane Michael, but there are natural questions about, does this happen for other storms, right? And this is kind of a difficult question to ask, right? Because how many times do we have storms interact with each other? Do we have data underneath storms to be able to ask those questions? And so, in terms of storm interaction, we were lucky to have hurricane season 2020. For those of you who don't remember, it was an absolute mess, right? And if you look at the Gulf of Mexico, I mean, it is a spaghetti plot of tangled roots there. I mean, it was such an intense period for the Gulf of Mexico that they actually had to do a blow up of the Gulf of Mexico to show the Louisiana area to clearly see what was going on there. And so in the Gulf, there were nine storms made landfall, which was a record, 2 as major hurricanes. So this was an absolute just chaotic hurricane season. And so as the title of my talk, which one of these storms do I want to look at? Well, it turns out I want to look at Sally for a couple different reasons. Primarily because we had data underneath it, right? And data underneath a tropical storm is not an easy thing to get, right? These storms are big, they wreck things, and they're fast moving and hard to predict. So it's hard to get instrumentation underneath a storm. But we have the benefit of our ocean observing systems in coastal Alabama, some of which DISL is running. And so the ones that what I am particularly interested in for this study was our offshore site CP or site focal or WECP. That goes by a couple different names. I usually just call it CP because it's the shortest acronym we have out there for it. Dolphin Island Sea Lab, our weather station, as well as NOAA's weather station, and NOAA's Orange Beach buoy are all really good data sources for this, for studying Hurricane Sally. And so this is sort of just a picture of the mooring site, right? We have a number of different thermistors throughout the water column. There's a surface and bottom CTD, then there's an ADCP that collects water column velocities or velocities throughout the water column. And so basically, we're going to use this data to examine the subsurface structure under Hurricane Sally, or on the continental shelf before Sally should arrive. But before we get there, let's look at Hurricane Sally, right? So Hurricane Sally was a pretty cool storm, right? So this is atmospheric model data from that basically, it's kind of a busy slide. So let me just kind of go through the different parts, right? The coloration is wind magnitude. The arrows are wind vectors that show magnitude and direction. We have a dashed line running through the center of that plot. That dashed line is the track of Hurricane Sally. We have a circle around a dot The dot is the low pressure center. The intensity of that low pressure is given in millibars, and that's the number 982. So the lower that number is, the more powerful the storm is going to be. And then the circle is the radius of maximum intensity. And so what you can see is the radius of maximum intensity is relatively co-located with that sort of peanut sort of area of brighter color. And so the model data is relatively consistent with the observational data that suggests where the radius of maximum intensity is. And so we'll just sort of walk through the evolution of the storm as it crossed the shelf. So it's crossing the shelf, it sort of intensifies, and then it sort of slams into the coast of Alabama. And so what to me was really shocking about this is just that rapid intensification where you go from, here to here, right? Where you can really see it amp up. You can see the symmetry in the storm form up, and it just becomes a really nasty storm as it's making landfall. And so that rapid intensification begins sort of in the magenta track there. On the top left is a picture of sea surface data, or satellite-derived sea surface temperature data. On September 15th, the day it was transiting the shelf, and basically the magenta is where it rapidly intensifies. And if you want to know more about what was going on the shelf during that time period, a recent paper just came out in JPO that talks about that story. But for this story, we're going to focus on the initial conditions, as I've mentioned. And so the question might be, why care so much about Hurricane Sally, other than that fact that locally it was a big deal? In a general sense, Sally is a really interesting story to look at because it rapidly intensified over the shelf, right? So this is not something that typically happens with storms. When storms interact with coastlines, they typically weaken. So Sally did something, I wouldn't say totally unusual, but just not common. The other thing that's really interesting about Sally is that for those of us that were here and probably were watching the NOAA forecast, this was a really difficult storm to forecast. And the predictions changed pretty dramatically, both in where it was going to make landfall, as well as its intensity. And so right here is a little plot of just a smattering of models, model forecasts. And this is 27 hours before Sally made landfall, right? So if you need to get up and go, you don't have a whole lot of time to get out the door with 27 hours left on the clock, right? And so all the models from this sort of sampling suggest the storm was either going to stay the same strength or weaken as it was making landfall. And so this is sort of problematic in the forecasting community, because in order to get the public to respond to things, you need to have informed and accurate forecasts. Forecasting is difficult. I don't want to give NOAA a hard time because this is a really challenging problem, and we're trying to do, and they're trying to do better, but this is one case where the models didn't really get it right. And so this presents a really interesting case study as to try to come up with clues as to what went wrong with the models. And we can get some insight on that by looking at the observations. And so as I mentioned, I want to focus on the initial conditions, sort of what was the initial environment that Sally had to work with when it made landfall. And so we can do that by looking at data. So the top plot is a sea surface satellite image from September 13th. And you can see that uniformly across the shelf, it's yellowy, greeny, like above 29C. And the plot here, what we're seeing here is a time series. So we go from August to September 17th or so. And so Sally makes landfall the morning local time, September 16th. And so that's highlighted by the little triangle. The dashed red line sort of just bring that sort of triangle down so you can kind of see where it lines up with the lines. And then the y-axis is temperature. And I'll note, right, so the temperature range here is 31 to 26.5, right? And so those of you might in the audience that are not familiar with hurricane research, you might say, well, 4 degrees, whatever, like what that doesn't really, it's kind of a small number in terms of temperature. But a lot of research suggests that as little as 1 degree temperature change in sea surface temperature can have a significant impact on intensification, right? So all we really need is 1 degree to make a difference in terms of intensification. So that 4 degree range there is important. The other thing to note is that prior to Hurricane Sally, where I sort of have that arrow coming down, you see this big, tall blob of warm temperatures, right? This turned out to be the peak. So the red line is the 2020 depth average temperature. Depth average temperature in the coastal zone is a good proxy for heat content. And what we're seeing is the annual peak occurring right before Sally makes landfall. And so to put this in perspective, because we have a long time series from the site, we can do the mean. So there's the 15-year mean in black. And then if we want to talk about extreme events, we can look at the 90th percentile, and that's in the dashed lines. And what you can see is this blob doesn't quite make extreme levels, but it's certainly above average, right? So we're working with a warm water mass here. The other thing to note is another sort of reference point is 28C. So there have been studies that have shown that 28C is associated with rapid intensification. It doesn't necessarily cause rapid intensification, but if you're going to get rapid intensification, you're probably going to see water temperatures at or above 28C, right? So that 28C is an important marker to keep track of, and we're a good 1.5 degrees above that 28C. So we're in sort of prime state here where intensification, the ocean is favorable for intensification, right? So the question that I sort of am asking is, how did we get to that state before Sally makes landfall? And I think what might be hopefully clear from this plot is the red line has these sort of clear bursts, upward bursts in mid-August and then basically early September, right? So we see these two big slopes of temperature increase as we're approaching Hurricane Sally's interaction. And so the natural question for me was, what's causing these two increases in temperature? Is it something that we can use for potential forecast purposes? And so the first story here, the first increase, you'll see a little triangular hash there. Hopefully that indicates to you guys there's something happening there, and it turns out to be a tropical cyclone. So this was the passage of Hurricane Marco. And so the top plot there, we see Sally with the circles indicated by the circles, and we see Marco's path indicated by the triangles, right? So Marco kind of swings through this area, and if we remember back to our initial sort of hypothesis, right? We have our cartoon structure here where what do we need for this sort of extreme heat content? We need a mixing event. So the question naturally is, did Marco create mixing in the coastal ocean? And so if we look at plots here, again, the bottom line is time. So we're going from August to mid-September. The top plot is the temperature plot we've been looking at. The middle plot is winds, wind speed, and the bottom plot is a color contour plot of the thermal structure of the ocean, right? So yellowy colors are very warm conditions, blue colors are very cold conditions. And the important thing to see here is when Marco makes landfall, indicated by that triangular hash, we see a negative blip of wind, right? So that blip jumps up to about 10 meters per second, which is pretty strong. So we have downwelling favorable winds that could potentially cause mixing. But before we can say that mixing was happening, we need to think about, and I will say that that blip of wind corresponds with a homogenization of the shell waters, right? So this water column goes from yellow at the top, blue at the bottom, to this homogenized sort of yellowy green color, right? So we do see a uniform water column here that we would expect from a mixing event. But before we can call it a mixing event, we have to think about how downwellings work, right? So if we look at a downwelling, for folks that are not familiar, this is kind of like a cartoony-like structure, where the top plot is sort of the initial state where we have a stratified water column, warm layer on top, cold layer below, and when wind blows along the shelf, there's something called Ekman transport that moves water to the right of the wind direction. So when we have an east wind in this area, water moves onshore, it piles up the coast, and starts moving downward and offshore, right? And that's what you're seeing in the bottom plot. As the evolution of this downwelling continues, that warm layer is pushing water onshore, that onshore water is moving down and pushing the pit decline down and bending it offshore. And that effectively moves the cold layer offshore, right? So there's this cold pool that gets pushed further offshore. And so this is a question of, are we eradicating the cold pool because we're mixing it out, or are we just pushing it offshore? And that difference matters because if we're just pushing it offshore, it can just slosh back when the wind relaxes and you're back to your cold, and you have your cold pool back, right? And so what we can look at in the temperature structure is if we compare before Marco to after Marco, right? The warm layer, that yellowy layer, after Marco is about twice as deep as it was before Marco, right? So you can still see some blue at the bottom there, but that warm layer goes from 7 meters to about 14 meters. So it's definitely suggestive of mixing, but we can do a little bit better than that. We have velocity data and we have water column hydrographic data. So we can actually do some calculations. We can look at something called the Richardson number, right? So the Richardson number, I know, never put equations in a presentation. This is a very simple one, right? This is just, we're looking at n squared over s squared, which is effectively stratification on top, mixing underneath it, right? So this is a ratio. So if we're above 1, stratification wins. If we're below 1, mixing wins. And the lower we are below 1, the more mixing we might expect, and the higher we are above 1, the more stratified it's going to be, right? So if we take the time period around Hurricane Marco and we expand that out and look at the bulk Richardson number, so that's what you're seeing in the bottom plot, the bulk Richardson number going from 0 to 4. I cut it off because we don't really care when it's really, really stratified. We want to be able to see if there was mixing, and so we want to look at values below 1. And what you can see is during Marco, so right around that triangle and just before that triangle, we see that the water column bulk Richardson number drops to around 0.25, which is well below 1. 0.25 is kind of like where we typically expect a lot of mixing to be happening. And so we do see evidence of mixing here. So if we go back to our little plot here, we have our stratified water column, baby storm comes through, and we have evidence of mixing here. So the next part of this is, do we have a period of warming that can heighten the temperature structure in the upper water column? And if you look at the temperature structure, you kind of can see little wisps of warming at the upper ocean. So there is some circumstantial evidence from the temperature data that upper ocean after Marco starts heating up. You can see kind of flashes of yellow, which is the diurnal signal, heating during the day, cooling off at night. But we can do a little better than that. We can look at heat fluxes. So the bottom plot here is heat fluxes during this sort of period of potential warming, right? And so the blue is the hourly, so you can see the daily oscillation. Sun comes out, things warm up, sun goes down, heat gets fluxed out of the ocean, right? That's what you're seeing in the blue. If you average over those days, you see that black line, the black dashed line is the daily average of the heat fluxes. And in that period that I've highlighted there, you have heat fluxes that are generally positive. Positive heat flux means energy is going into the ocean, and you would expect the ocean to be warm. So that's check, right? We have our two parts. We have our two parts here, right? We have our mixing event, and then we have our subsequent warming event. And so let's look at how that translates into the depth average temperature, right? So let's go back to our temperature structure, and we can see after Marco, we don't have a rapid warming, but we have a persistent level of heat. There's a little bit of warming there. In the tail end, we see a little drop off. At the end of that box, the heat drops, the temperature drops a little bit there. And this is basically because of the wind conditions have switched from upwelling, from downwelling to upwelling. In upwelling, you expect colder bottom water to be coming inshore. And so effectively, the upper ocean heating is fighting this blob of this water mass that's trying to evect back on shore. And so Marco does mix, but it doesn't mix the shelf out completely. And that can be seen from that cold blob. And so we do get some mixing from Marco, but there's still some cold water left on the shelf. So it's not a complete clearing of the cold pool. So the next question is, well, what's responsible for this last little blip, this extra degree of heating that pushes into to take us from average to above average? And so this last blip, if we look at the wind data, what jumps out is we see another downwelling event. And this is a persistent downwelling. This is about 10 days of downwelling favorable winds. And if we go back to our cartoon of downwelling, what would we expect to happen? Well, we would expect water to be going onshore at the surface, warmer surface water, pushing water down and offshore, moving the cold pool offshore. And that's basically what you see here in the bottom plot. There's this persistent downwelling that you can see the blue area on the bottom of the water column is basically disappears from the data. And that's consistent with the front pushing offshore and moving that cold pool offshore. And so the question we now have to ask is, how far does that cold pool go offshore, right? as we have this storm approaching, the question is the shelf, has that downwelling event pushed that cold pool completely off the shelf, and so we don't have to worry about it? Or is it only maybe a couple kilometers from the mooring site? And so since we don't have data beyond the mooring site, we have to rely on yet another equation. Sorry, I'll summarize what this does. This is basically a way in which we can use wind speed and the slope of the continental shelf to predict where that the front of that warm pocket should go out to. And so if we do the calculation, what we see is that this the front of this downwelling should get out to about the 50 or 60 meter isobath. So it gets more than halfway off the shelf, right? And this is using the 28-degree isotherm. So inshore of that dashed line, all the water is expected to be above 28C, right? So this is basically a runway for a storm to intensify. And so to summarize this, basically, what do we have going on here? Well, we have a sequence of events, both of which are associated with downwelling, right? We have Hurricane Marco that has downwelling winds that mix the water column, and that's followed by an unusually long duration downwelling that pushes the remnants of what's left of the cold pool nearly off the shelf, right? So this combination of effects have left the shelf relatively homogenized and relatively warm. And so because both of these events have downwelling playing a big role, I got to thinking, was this sort of just a freakish time when we had a lot of downwelling? Was this kind of just an anomalous downwelling condition and not normal? And so how do we investigate that? Well, we find some historical data and look to see what the wind conditions were like during this time period in other years. And so if we do that by looking at the Orange Beach buoy, which goes back about 10 years, and the Dolphin Island NOAA station, which goes back to 1987, right? And if we look at, this is sort of a plot of wind stress, and what we want to focus in on is the negative nature of this. Negative means it's coming out of the east, blowing to the west, which is downwelling favorable. And if we look at every single year during the time period between August 15th and September 14th, every single year, it's 0 or less, right? Always negative. And if we look at 2020, so at the end of that plot, in red, the Orange Beach buoy, it does look like it's high at the Orange Beach buoy, but if you compare that to other years like 2012, 2007, 2005, these are other years where we have equally high levels of downwelling winds during this time period. So this isn't really extreme. This is kind of the normal, right? So we have normally during this time period, we have downwelling. So the next question is, well, if we have downwelling winds, do we typically see warmer waters offshore, right? Because that's what's going to be coming in. That's going to be filling the inner shelf and pushing the cold pool offshore. So if we look at the climatology of temperature measurements, right? So this is called a home-over diagram. And what we've done is I've taken a slice of satellite imagery, starting from basically Mobile Bay and going offshore past the shelf break. The dashed line is where focal is. The other black dashed line going across there is where the shelf break is. And what I hope you can see is in the 30 degrees latitude, so we have degree latitude date going across the x axis. And what I hope you can see is as you transition from summer to fall, there's all red uniformly across the shelf in the beginning of August. And what you can see hopefully is the top starts changing faster than the offshore conditions, right? So if you go up on, say, September 1st, it's reddish to orange. And so the red is offshore, the orange is inshore. So there's this temperature gradient where offshore tends to be warmer. You can clearly, I think you can clearly see it once you get to October, where it's yellowy orange and blue by the coast, right? So there's this temperature gradient where you have offshore temperatures that are maintaining their temperature, their high temperature conditions, inshore conditions, which get cooler fast. Right, so you couple that with the downwelling, that's going to be pushing warmer offshore water to the shelf, right? And so we have a coupling here of climatologies. We have downwelling favorable winds coupled with temperature conditions, which could lead to statistical likelihoods of there being a downwelling that's going to warm the shelf and provide sort of a runway for hurricane intensification. So this is our local scale, right? And this is sort of, more limited sort of data. If we look at wind conditions over a broader area, say the whole Gulf of Mexico, and we look at how likely downwelling is is to be happening during the peak of hurricane season. So August, September, and October, actually like August 15th to October 15th, right? If we look at the peak period there, what we can see is the red is where we would expect downwelling favorable conditions. And a lot of the Gulf Coast is pretty red, right? So this tells us that during hurricane season, we typically have a lot of downwelling favorable winds, which is conducive to setting up shells in a way that's favorable for rapid intensification. So the work suggests that some coastal regions have enhanced risks from downwelling conditions. So to summarize, the annual peak and depth average temperature occurred prior to Hurricane Sally transiting the shelf, leading to very favorable conditions for intensification. If we look at the depth average temperature, how we got there, we saw a distinct cascade of weather events that included both cases persistent downwelling. The first increase in temperature was associated with Hurricane Marco, which homogenized the water column to some extent and created some mixing, which pushed heat downward. And that was followed by a persistent downwelling that pushed any remaining pocket of cold pool offshore, or at least further offshore. And then we sort of broaden this out to not just focus on Hurricane Sally, but if we look at the climatological conditions, there are areas that, particularly the Gulf of Mexico, that are likely to have this happen during peak hurricane season. And so there are these hot spots for effective warming during over the shelf during peak hurricane season. And so this presents an additional risk factor for coastal zones that may not be accounted for. Okay, with that, I will just let you know, all this work is sort of out in the literature in a series of papers since 2021. And that's a picture of the island after Hurricane Sally. And so hurricanes are important, and understanding how they get and do what they do and get to the strength that they get to are significant issues that we're working on. With that, happy to take questions.